Everybody get the notes for solutions, chapter 16? Come get it if you didn't get it. Sizable package, but a lot of this will go through in a fairly expeditious fashion. Given that we considered a fair amount of this in the last chapter on liquids. X3 scores, both tomorrow on the key. How was X3? Okay? So. Good. Now, solution. There's some comments which we shared with you way back at the start of the term when we talked about matter and all the various forms thereof. The solution is obviously a sample of matter, specifically a homogeneous mixture. Mixture, guaranteed that the solution is composed of at least two components. One or more solutes, the stuff dissolved, and the solvent. In most cases, the solvent is the principal component of a solution. Like for these aqueous solutions which we've listed here. Solutions with which you are familiar as a consequence of dealing with them in the laboratory. Sometimes, however, if, for example, you combine miscible liquids like water and ethanol, water and methanol, an investigation you made on solutions in 45 laboratory districts. Determining which material is solute and which material is solvent is really not possible if, for example, you put together an equal volume mix of methanol and water, or any two miscible liquids. Remember what miscible means? Miscible means regardless of how much of each liquid you use in making the liquid solution, you'll get strictly a solution. You'll never get phase separation. These materials are perfectly, entirely soluble in each other regardless of by volume proportion in which they're combined. So if I make an equal volume mix of methanol and water, it becomes arbitrary which one you wish to identify as the solvent. There are solid phase solutions. Ross. Hybridizing brass and bronze. Ross. Brass and bronze. Pewter. Dental. Gas. I think air is the simplest example of a gas phase solution. Provided the air in question, free of dust, pollen, fog, smog, smoke. I'd say the air in our classroom is a good example of a gas phase solution. But arguably the most important type of solution, at least at this stage of the game, given that these are the solutions with which you deal most commonly in laboratory, liquid solutions with liquid solvent. Example, 1 molar sodium chloride, 1 molar HCl, 1 molar sodium hydroxide, 1 molar acetic acid, tap water, gasoline, beer, pot. We could make a list that's of great light, that's not a consequence. Now, of far greater consequence are the types of interparticle attraction forces which we encounter in liquid solution. So this is the aspect of liquid solutions which really we already considered in chapter 15. But since it's germane to this chapter, or so obviously, I've re-included it in chapter 16 notes. I've listed all the interparticle attraction forces. Ion-ion, ion dipole, hydrogen bonding. Hydrogen bonding again exhibited by molecules which have one or more OH groups in their composition, and or one or more NH groups in their composition. and the HF molecule itself, and to some extent, the HCl molecule. So as you've recognized in preparing for exam 3, to identify a molecule capable of hydrogen bonding, you need to look at its Lewis structure. See if it is composed of these linkages. Dipole-dipole. IAFs exhibited by molecules which are permanently polar. Well, polar molecules can induce dipoles in non-polar molecules. And induced dipole, the type of interparticle attraction force shown by all material. London stuff. So a question. 16.1. Aqueous sodium chloride solution. Aqueous calcium carbonate solution. Two solutions with which you have dealt in lab this term. In which of these solutions do you find the stronger ion dipole attractions? In which of these solutions do you find the stronger ion dipole attractions? Calcium carbonate solution, the sodium chloride solution. How many vote for sodium chloride solution? No looking around. If there's any unfair play in this election, it will be conducted by me, because I'm running the election. And I won't play unfair. Okay? I'm strictly the vote count. Anybody vote for sodium chloride solution? Hands up high. 3 million points off if you don't vote. How many vote for calcium carbonate solution? Most votes cast for the calcium carbonate solution, which is correct. Why so? Well, the dipole is common to each solution, isn't it? It's the water molecule. So the question is, will the water molecule associate more strongly with a sodium ion and or a chloride ion, or with a calcium ion and or a carbonate ion? Calcium ion. More so than sodium ion. Why? Calcium ion is twice as plus. Carbonate ion. Twice as minus as chloride ion. Well, if the ion dipole forces are stronger in aqueous calcium carbonate solution, why is this stuff so much more soluble? You knew there had to be a bite to this question. You just told me, and you were right. The ion dipole attraction forces are assuredly stronger in saturated calcium carbonate solution. Okay, never mind, saturated calcium carbonate solution. So why is sodium chloride a whole lot more soluble?
Because their ion dipole forces are weaker, and so it's easier to break them apart.
Well, if the ion dipole forces are weaker in the sodium chloride solution, which they are, and that was the only part of the puzzle you had to consider, you'd expect calcium carbonate to be more soluble in water. Do you recall the experiment in which you investigated the water solubility of calcium carbonate crystal? In lab? Which assignment was it? I wish the lab course was run the way it was supposed to be run, and then you people come to class knowing about this stuff. Because you'd have to do it on an individual basis. Then you'd be required to pay attention. It's not your fault. Carped about this before, now I'm carping about it again. It's a doggone shame when enrollment requirements overrule educational demands. Something is out of whack here. In assignment 4, you are asked to observe conductivity of sodium carbonate solution and calcium chloride solution. With your handheld conductivity meters, you found out that these materials gave off-scale readings. The ion concentrations were far too great. Then you are asked to mix these solutions. And on so doing, wham, out fell this white solid. What was this white solid that fell out? There it is. Teacher's favorite weapon. There's other stuff in here besides calcium ions and carbonate ions, but it's mainly calcium ions and carbonate ions. I think analysis for this brain stuff, which I like, is about 95% pure calcium carbonate. I like that. And then you were asked to filter in order to separate the calcium carbonate precipitate you had just prepared from the solution portion of this mixture. Then you were asked to take the calcium carbonate, which you had on the filter paper, and wash it. That didn't mean you got out a scrub brush with soap and did that to it. You didn't get out your loofah and rub it. You took your squirt bottle with the ionized water and squirted it in order to remove the solution part of the mixture, which still remained on the surface of the calcium carbonate you had just formed. Then you're asked to transfer some of this calcium carbonate you had just formed from the filter paper, put it in a small beaker, add about 50 milliliters of the ionized water, and stir it thoroughly. Now, by this stage of the game, you had already observed with your handheld conductivity meters that the laboratory deionized water did or did not show a conductivity. Did not. The conductivity meters are insufficiently sensitive to pick up the very tiny ion concentrations in pure water. 10 to minus 7 molar hydronium ion along with 10 to minus 7 molar hydroxide. But after you prepared this saturated calcium carbonate solution, because when you took this small part of calcium carbonate and stirred it up into 50 mils of the ionized water, all I'm doing is re-describing what you asked the rest of them like. Stir it thoroughly. You saw that some of the calcium carbonate remained undissolved, even though the amount of water was now far greater than the amount of calcium carbonate with which it was mixed. And then reobserve conductivity. On reobserving conductivity of saturated calcium carbonate solution, did you or did you not now see a conductivity reading on the meter? Yes, you did. Wasn't large, but you saw it. So this told you that on making the calcium carbonate deionized water mixture, some of the calcium carbonate had to dissolve, because the mixture showed a greater conductivity than pure water itself, but not much dissolved. Because in considering this question, you had so far focused on the ion dipole forces, but you didn't think about these. If you're going to analyze solution behavior, you have to pay attention to all the interparticle attraction forces of consequence which are present in the solution system. Right? Because although calcium ion water dipole interactions are stronger attraction forces than our sodium ion water dipole, just like carbonate ion water dipole attractions are stronger than chloride ion water dipole. Calcium ions and carbonate ions stick together a whole lot more strongly than do sodium ions and chloride ions, and that overrules, because from a relative strength standpoint, because I purposely wrote these forces in order of strength in general. Strongest, next strongest, and generally weakest. Now sometimes molar mass will overrule, like iodine is a solid, even though it's a non-polar diatomic, homonuclear diatomic material. It's got a very large formula mass, so the London forces are extreme. So, again, you want to pay attention to solution behavior. Pay attention to all the interparticle attraction forces of consequence which exist in the solution that you're asked to consider. All right? 16.3. 16.2 is something we need to deal with at this stage of the game. Something we're already doing. I've listed the solutions in question in order of increasing boiling point. Why so? Why does this solution have a lower boiling point than this solution? What is that?
Sucrose,
Sucrose London forces. Wait a minute. What do you know about sucrose? Are at all familiar with sucrose? Table sugar. You find table sugar to be fairly soluble in water? Quite soluble in water? Did you do some investigations in 45 lab in the solutions assignment this term with table sugar? And me, being the nasty person that I am, expect you to know all this. And if you did that on an individual basis, and you're a good student, you would. But with this team nonsense, we can't get there. Now then, given that you were asked to deal with sucrose in the lab, in pure sucrose, pure table sugar, what are the principal intermolecular attraction forces? What are they? This stuff is also discussed in the notes. The principal interparticle attraction forces shown by sucrose molecules or other sucrose molecules. What are they?
Dipole bond. Hydrogen bond.
How about that? Because along the string of carbon atoms, which constitute the molecular skeleton of this molecule, you find an OH group connected to these carbon atoms. Sugar molecules are notoriously good hydrogen bonders. I mean, you ought to recognize something's going on here, given that you see sugar to be so soluble in water. London forces, there was only London forces. You think that material which shows principally London forces and which is a solid under normal laboratory conditions is going to be considerably soluble in water? Did you find iodine to be considerably soluble in water because in the solutions experiment you did business with that too? Iodine, very slightly soluble in water at most. But sucrose, whew. I probably would get some of the OH bonds in the wrong place, but you got, let me see, C12, H22O11, so you got 12 carbon. You know, it's all zigzag, they're all SP, let's see. Is that an aldose? Anybody remember? I don't know if it's an aldose. Aldose means one of the carbons got a carbon on a double bond.
Sucrose.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And on and on and on and on. You can put an OH group on every one of these carbons, but some of them are up relative to others being down. And you can learn about optical activity of asymmetric carbons and a bunch of stuff, which we should have talked about this term, but it wasn't considered fair game by my colleagues. So we won. Do you recall my asking you to consider optically active molecules with your work in assignment 6 in the lab? I find it interesting that the lab asks you to go a lot further with these considerations than the lecture. So it makes sense to me. In any case, you can look up sucrose on your own. So, back to this. In 0.8 molar sucrose solution, 1 liter, let's imagine we got 1 liter of each of these. 1 liter each. How many moles of particles? 0.8. How many moles of particles here? How many moles of particles in this? 1. How many moles of particles in this? 2. How many moles of particles in this? Why does this have a higher boiling point than this? Is magnesium ion twice as plus as sodium ion? Sulfate ion twice as minus as chloride ion? These attract water molecules more strongly than sodium ion and chloride ion? which means boiling point elevation for this solution will exceed boiling point elevation for this solution, which is part and parcel of what we shall be discussing in this chapter, called colligative properties. More on that later. And then 0.5 molar aluminum sulfate solution. With 0.5 molar aluminum sulfate solution is the highest boiling point of this collection of solutions. Water to solvent for each case. Think you might have a higher concentration of ions in this solution than the other one? This is 2 molar in particles, isn't it? What's the molarity of this in particles? Dissolved particles. Ions. Remember talking about total ion concentration with the work you did in lab? Because conductivity depends on total ion concentration. And other things. But for the first approximation, the concentration of a solution, partly the conductivity of a solution, will depend on its total ion concentration. And then everything gets all more complicated when you think about acid solutions and base solutions and the ability of water molecules to transfer H+, and the ability of water molecules to transfer hydroxide ions among them between themselves, and magnifying conductivity effects and stuff like that. But I ask you to consider all that stuff with your work in assignment 4. Because, hey, in chemistry you learn how material behaves, aren't you? So ion concentration for this solution. Was it? 2.5. See this? So this solution is 1 molar in aluminum ions and 1.5 molar in sulfate ions. All right? Solubility, a couple comments. First, the term itself is a loaded term. And if I'm going to define solubility limits, I have to tell you what they are because it's an arbitrary sort of thing. So I'm sticking with what was given me when I learned this stuff way long ago. Go back there and they're still finding out things about my family with archaeological digs and things like that. When I was 9 years old, a friend of mine said, "We have a TV." And invited me to come to his house. See the TV. I remember it was a Philips. And a 9-inch round screen like this. And we peered at it. The picture was fuzzy and blurry, but it was a TV. It didn't TV too good, but it was a TV. So, on developing a saturated solution, compounds are commonly considered to be soluble if the saturated solution molarity is 200 molar or above. Now, students have a habit of misinterpreting this word soluble. I see this going on in 46 laboratory all the time. I mean, if you think the word soluble means that I can take a given quantity of a so-called soluble material like sodium chloride and dissolve it in water regardless of the relative percentages of each component of the system. I mean, do you really think you can take a pound of sodium chloride, dissolve it in a drop of water? Pound of table sugar, dissolve it in a cup of tea. You can't do this. The student says, "It's soluble. Why didn't it all dissolve?" How much solid did you use? How much solvent did you use? Well, I used a half a packet in a quarter of a milliliter. So I have to say more. 0.02 molar to 1,000 molar, moderately soluble, and at saturation, if the molarity is less than 1,000 molar, The material is generally referred to as sparingly or slightly soluble. So with that, I will tell you, I believe I told you this before, but I'll tell you again. You better watch out for this word, insoluble. Because you know what, students, if they don't think, you know what they take that word to mean? That means no dissolving, period, none, absolutely zero zip. That's not true. Any material, I don't care what it is dissolvable to a certain extent in any liquid, I don't care what it is. But if you can't find out how much stuff dissolved by making measurement, it's fair to say it's insoluble. I told you the story, I believe, about the tin being dissolved in water earlier on in the term, as an excellent example of material which I think would be fairly classified as insoluble. So just for fun. Because this is a true story. I don't know how the chemist did the arithmetic to answer the question, but presumably chemists took a bunch of pulverized tin, stirred it vigorously in water, filtered to remove the undissolved tin, and now the solution was saturated tin solution with water being dissolved. So we shall imagine that we have, we're going to isolate 1 liter of this solution. Saturated tin solution. And then, this is part of the puzzle, I don't know how it was done, but the chemist reported that his analysis of the system showed that only 1 tin atom, only 1, had dissolved in the liter volume of system. Only 1. So what I like to do is to say, okay, we have this 1 liter saturated tin solution, and I pour 500 milliliters into a glass, and I give you the glass, and I keep the rest, and I say, who's got the tin? I defy you to answer that question. Because I don't know what kind of analysis you could do to find out this 1 tin atom in the portion of solution you have versus the portion of solution which I have. Now then, observation. Because when we have a solution saturated with a solute, we have this condition. And you are asked to consider this condition with your working laboratory this term. What's this stand for? Equilibrium. And in 2046, at least the way I run it, we are analyzing equilibrium systems throughout. That's what you do in 46 laboratory. Equilibrium is something which chemists must know how to deal with. Because you're trying to make a particular yield, if you need to get 80% conversion of reactant to product, and the reaction you're running, which is the only reaction you're aware of, under the best conditions you know of, only gives you 40% yield, well, then you've got to fight this. On occasion, and on many occasions, frankly, and you became familiar with some of that stuff this term in lab, particularly the solutions experiment. You can look at a chemical system and recognize whether or not equilibrium may be existing in the system between solute and solvent. So let's consider 3 systems. Calcium sulfate dihydrate, common name gypsum. Are you all familiar with gypsum? Anybody familiar with gypsum? It's the main ingredient in what? Drywall. When you do wall fixing at home, anything like that, or help anybody do any simple construction, things like that? Plasterboard, sheetrock, whatever you want to call it. Okay? So let's imagine that I go home some of this stuff. So I punched a hole in your wall. I'm gonna pick up the crumbles, and I'm gonna shake it in the ionized water. I'm shaking with, say, a bathtub full of deionized water. Can I or can I not make an observation which will allow me to tell whether or not this equilibrium exists after having made the mixture and agitated it thoroughly for a good long time? Can I make an observation which will give me the opportunity to conclude that this equilibrium exists in your bathtub where I smashed your wall to get the sheetrock?
Yes.
While running feverishly to get away from your parents, who are not happy with me after having destroyed one of their walls. Okay. See, I went into the bathroom, filled up the bathtub with water, and we locked the door. I said, look, we're doing the experiment in here, don't bother us. Never mind the fact that I ruined your wall. I'll send the bill to UF administration. They seem to be of a mind to spend money on strange projects. What observation could you make to conclude that that equilibrium existed? You know what sheetrock looks like? White solid, crystalline, but the crystals in the solid are very tiny, look more like a powder to you probably. What observation would you make?
You would observe that the solution will reach equilibrium when the gypsum stopped dissolving.
Yes! So if I ask you to make saturated sucrose solution with your table sugar at home, you take some water and keep adding sucrose with stirring until you see by observation that added sucrose no longer dissolves. Now you got the equilibrium. So here, the solute is a solid. The solution is liquid part, is liquid. So I can recognize the possibility for this existing when I see undissolved solid present in the mixture, okay? Well, now here's a system which I asked you to prepare in laboratory this term. At the start of the solutions experiment, I asked you to make a mixture of hexane with water. Remember that? Do you remember hexane is of the formula C6H14? It's a hydrocarbon, and it is consequently polar, yes or no? If my memory is right, you took 2 milliliters of water, 2 milliliters of hexane, something like that, put it in a test tube, stopper tube, and shook, agitate it thoroughly. And then you allow the system to settle. And after settling, did this equilibrium exist? Yes or no? How many say this equilibrium did not exist? I mean, you did the experiment. I've asked a bunch of graduate student trainees this question, and most of them said, no, equilibrium didn't exist. I said, did you not take hexane and water and shake them to eat with each other thoroughly? Do you not think this maximized the dissolving of hexane into the water portion and water into the hexane portion? Well, then that equilibrium exists, doesn't it? You just made it exist. Of course. You see this interface. So what? In so doing and making the mixture, you saturate hexane with water and simultaneously water with hexane in it. So the equilibrium exists. Remember, liquids are dynamic. They're in motion. Don't let me trick you. Don't let me bully you. Now then, are you familiar with this equilibrium? Simply put, you got any of this stuff going? Commonly used to make salad dressings. Commonly used in various cooking practices. You've got dirty mirrors. Spritz some of this on a mirror. Wad up newspaper. Just wad it up. I mean that, clean that mirror, like make it shiny, sparkly, don't leave it. Simple way to clean a mirror. Well, in that vinegar solution, this equilibrium exists. Dissolved acetic acid, which have not reacted, dissolved acetic acid molecules, in combination with water and solvent, but some of the acetic acid molecules react with water and solvent, produce hydronium acetate ion, and you'll pursue study of this equilibrium extensively in 2046 and 2046 lab. In fact, in the first assignment of 2046 lab, you will investigate this equilibrium. The question is, by observation, can you recognize the presence of this equilibrium in a test tube or a beaker? Do you know that the physical appearance of this liquid, of this system, is that it's strictly a colorless liquid? I got a colorless liquid in my cup. Does that equilibrium exist in my cup? I'm looking at it. Would you like to look at it and comment as to whether or not that equilibrium exists in this cup?
Yes.
He claims the equilibrium exists in my cup. I'm not fond of drinking vinegar.
But there is still some acetate that's going to be in there for metabolism.
The problem is,
It's
the
just,
system is strictly homogeneous. You see what happened with these other systems? Heterogeneous, two-phase system. Heterogeneous, two-phase system. When you have a one-phase equilibrium system, by observation, you cannot recognize whether or not the equilibrium exists at all. It may. And of course, there's ways experimental ways by which you can find this out. But by observation, eyeball observation, that won't do. Now then, we now broach a subject which astonishingly, I'm astonished by this, the Silverberg text actually considers. The thermodynamics of dissolving. Now, I don't know how he expects to consider this in an effective fashion, since prior to this chapter, in section 13.3 where he discusses this, he's not yet said anything about entropy, nor has he said anything about free energy, which he should have done early on in chapter 5 or 6. You heard me preach about this before. But here it is. And I've already looked to see what he has. He got some shortcomings in there. But I don't care, because I'm not talking from the basis of what he offers in his text. I am talking from the basis of what I asked you folks to consider in the lab in assignment 7 on solutions. Remember that? Thermodynamics of dissolving? It's all in there. So, I am going to now outline the parts of this puzzle, and we will continue with this conversation tomorrow in discussion class. Consider the aqueous dissolving a sodium chloride whole. Which is represented by this simple reaction statement, one we've seen many times before. Now, do you remember we didn't speak about this extensively, but we did speak about it. I introduced you to delta G and delta G0 back in chapter 5 or 6 of our notes. Where we took as a given very important fundamental thermodynamic relationship and change in free energy for a process, in this case the process is dissolving, is equal to change in enthalpy for the process minus the temperature in Kelvin at which the process is taking place times the change in entropy for the process. Do you remember that at that time, we talked about needing to know if the process is spontaneous. And we said, you can look at delta G for a process and get at spontaneous. If delta G is minus and not if delta G is plus. And if delta G equals 0, what condition exists? Do you remember? Okay. And we can write the same for delta G 0. The $64 issue, though, is to realize that delta G applies to any imaginable set of conditions. So until you specify the conditions, you can't say anything about delta G as to whether or not it's minus or plus. It's like if I put calcium carbonate in water. We just talked about this a while ago, didn't we? Some of the calcium carbonate dissolved, didn't it? Because the saturated calcium carbonate solution was more conductive than pure water itself. So, if it dissolved, all you did was put together the calcium carbonate with the water. Dissolving was spontaneous. Delta G was minus, and it was minus until saturation was achieved. So I'm kind of at a loss to be specific on this business of spontaneous if I look at it from a delta G standpoint, because it considers every imaginable set of conditions. So the preferred, at least from my point of view, preferred way to specify whether or not a process is spontaneous is from this. So the remaining consideration, if we get up from this point tomorrow, is, remember what this means? Standard state. So if this dissolving of sodium chloride is spontaneous from a delta G0 standpoint, then delta G0 for this is minus. What experiment did I ask you to do in the lab this term, assignment 7 solutions, to prove that sodium chloride dissolves spontaneously in water under normal lab conditions? What did I ask you to do? Anybody remember? We all have to go back to lab, apparently. Because if delta G0 solution for sodium chloride is minus, it means that saturated sodium chloride solution has a molarity which compares how to 1? It's what? It's what? Greater than 1! More soluble than 1 molar. How about that? So now we've got a specific reference point. Will the stuff in question dissolve to give me a saturated solution condition which exceeds 1 molar? If so, it dissolves spontaneously from a delta G0 standpoint. And what are the puzzle parts of the dissolving process? Delta H and delta S. Do you remember what you did in lab to find out if sodium chloride dissolves if it dissolves in water enthalpically favorable or not favorable? You measure the temperature of the system as sodium chloride dissolves in water. And what did you observe? Sodium chloride dissolves in water from associated with a slightly exo- endothermic change. What is it? Endo. And endo means it's not for it, it's a gimmick. So what part of the puzzle do you think causes sodium chloride to be dissolving? The delta S part, doesn't it? And then we're going to analyze these in detail tomorrow. We'll be there.